So in kinetics, the other part we need to understand is steady state approximation. How does it work? Steady state approximation is to make all the intermediate to be the rate of change of intermediate to be zero. For example, if you notice, this is the overall reaction and these are the respective reactions that have been happening, correct? So you can see here. So we could say that yeah, see this is the overall reaction and these are the steps in which the oxygen being the intermediate, the rate of change of oxygen has to be zero. So which means if you notice in the forward direction, I mean rate of change of oxygen, nascent oxygen, it is forming in the forward direction, it is moving away in the backward direction, and it is again moving away in the forward direction. So we can write whenever there is a gain towards the nascent oxygen, it is positive. Whenever it is a loss, it is always going to be negative. So you can see K1 into O3, K2 into O2 into O, K3 into O3 into O. That is equal to 0. Okay. So from here, we can get what is the concentration of the intermediate. And once you get the concentration, the second step is the rate determining step. So you'll always have to write the rate for this one. And from there, we can calculate what is the value of uh, nascent oxygen. Now, here is the important point. When it comes to an equation like this becomes very difficult to say whether it is a first order, second order, or anything. Correct? Clear? But if you compare this one, you know that K3 value is very, very small compared to K2. This is what we learned. So,
Yes.
which in front of this value, I can ignore this one. So, ignoring that, we will get this equation. So, which is exactly same equation as what we derived from the equilibrium method as well. Huh? So, you could notice that both the methods are actually giving the same idea. Hmm? Okay. Quickly go through this question which was asked earlier in the exam. Check. Next notice. Typically, when you have a reaction given like this, A plus B is giving this and 2C is given, this one is given, you need to check out what is the overall reaction here. Okay. Which are reactants, which are intermediates, which are catalysts. Okay. All those parts. So, when you add all of those steps, step 1, step 2, step 3, what is that you're finding out? You're finding that A and B, correct, were always being a part of the reactant side, isn't it? Hmm?
Yes.
And you can see F is getting formed and it is getting consumed as well, which means it must be an intermediate. F is an intermediate. Clear? Likewise, C is also an intermediate. Okay. While D is a product and G is a product.
Yes.
Okay. So therefore, we can say overall reaction is 3B giving 2G plus G and AB are reactants and A being catalyst, CF or reduction material. Done? Okay. What are the general statements we need to know? Every reaction has an order. Is it correct? Every reaction has an order. Okay. See, when we are saying every reaction has an order, that is not necessary. Got it? Okay. Next, partial orders are never negative. Partial orders are never negative. What is partial order means? Which means order with respect to one reactant. Clear? Can they be negative or not? Yes, they can be negative. Okay, earlier we got that O2 raised to power of minus 1. Yeah. Partial orders are always integers. Is it necessary? No, it can be fraction also. Rate constants have same dimension, not necessarily. Correct? And single step reaction order is equal to molecularity. Yes, because for elementary reaction, order and molecularity is same. Hmm? Next, zero order is always complex reaction. Yes, in fact, it is always complex. Rate constants are always positive values. That is always constant. Let me add you few more. What is overall order is always positive. Is it true? False.
True.
True. Overall order is always positive. Clear? Otherwise, reaction is not happening. Correct? Clear? Molecularity of a reaction can be 4.
False.
False. It cannot go beyond 3. Okay? Molecularity of a complex reaction is not defined. Yes, beta. Molecularity of a complex reaction is not defined. True.
True.
Molecularity of the overall reaction is never defined. Got
Mm.
it? But suppose if I tell you molecularity of an SN1 reaction is 1. Answer is yes or no? Yes, but it is a complex reaction. So how are you defining it? See, as long as molecularity of the overall reaction is concerned, there is nothing like that. But when we say SN1 or SN2, we are referring to one step in it. Clear? So yes, molecularity of that slowest step exists, but molecularity of the overall reaction does not exist. Clear, beta? Hmm.
Yes.
Let's see what is zero order reaction. Zero order reaction is when reactant has 0 power raised to power of 0. You bring it to the left hand side. Okay, this is anyway 0. So if at all I write rate in terms of rate of change of A, and then integrate that from initial concentration C naught to final concentration Ct over the time 0 to T, then you will get an equation Ct is equal to C naught minus Kt. Hmm? So this is
Yes.
the equation how the concentration is decreasing over time. Hmm? And next, time for completion. How much time does it take? Now, this is a time when C naught, when concentration C becomes 0. When this becomes 0, C naught is equal to Kt. Other important factor which we'll be always using is T50, that is half-life. T50 is when Ct is equal to C naught by 2. So half-life of zero order is C naught by 2K. Clear? What are
Yes.
the units of K? Check out that as well. Units of K. You can write it from here only. C naught by 2K, 2T, right?
Yes.
So which means it is mole per liter per second inverse. Hmm?
Yes.
That will be the units of K. What are the other important graphs in zero order? How the rate is changing with respect to concentration. Okay. And how T is changing with respect to concentration. Since it is a zero order, rate should not change. Okay. And when it comes to half-life with respect to different concentrations, you will see half-life keeps increasing for different concentrations being increased. Usually, a metal adsorbed catalytic reactions are zero order reactions. Okay, clear beta? So metal is absorbing some amount of gas and then some reaction is happening there, like Born-Haber process, hydrogenation reactions. Correct. So all these kind of reactions are generally uh, what type of reactions? Zero order reactions. Clear? Mm. Next 10, 5, 2.5, 1.25. Okay, so these are respective change in concentration of the reactant. So based on the data, what we can see initially from 10 to 5, 5 minutes. So if it is required, then 5 to 2.5, only 2.5 is required. 2.5 to 1.5, 1.25 is required. So this data suggests it is very much mapping with zero order kinetics. Clear beta? Just like how we write T half, we can write T 3 by 4 also, which means the amount that got consumed is 3 4 by A naught. Done. So that is equal to T, 3 by 4 is equal to 3 C naught by 4K. Hmm. Any doubt? Zero order. Check out first order. First order is about A giving products. A naught to AT. If I bring this A to the left hand side and integrate that, because at the last, see, when you bring it A to the left hand side here, so as it differentiate from here, you will get A naught into e raised to power of minus KT.
Yes.
Next, T can be written in terms of, AT and A naught, AT being the concentration at time T, A naught is the initial concentration. Okay, beta. So AT can be written as A naught minus X, and A naught minus X can also be introduced as A naught into e raised to power of minus KT. So if I introduce that, X will be equal to this much. Hmm. Time T is equal to ln2 by K of the reaction. And ln2 is 0.693 by K of the reaction here. So time 3 by 4th will be equal to AT is equal to A naught minus 3 by 4th of A naught, which is 1 by 4 A naught. So 75. So that means when it comes to 75% of the reaction is done. So that would uh, be equal to 2 raised to 2 times of T50. Is this clear, beta? How we got that? So if you have it for nth order, then we will write it as AT is equal to A naught by 1 minus A naught by N. Okay. I mean N times completed, not nth order, 1 by N times completed. Then this is the equation you will get. Now this might be something which is new and that might be asked, which is average life. What is the T average life? T average life is integral 0 to infinity Ct into Ct into dt. This is the total amount of uh, you know the Ct into T is, what is the concentration after every small amount of time. If I
Yes.
add all of them, like from 0 to infinity, that divided by the original amount of concentration, that means you are averaging it out, isn't it? So as you average out, this Ct can be written as this one into dt. Now if you integrate it, this value turns out to be 1 by K of the reaction. Done. And T average 1 by K of the reaction is T50 by ln2, which is
Yes.
equal to 1.44 T50. Now, quickly go through the graphs once. I hope you do understand the graphs easily. Please check. See, what's happening here is, that AT is equal to A naught e raised to power of minus KT. Okay.
Yes.
So if a reactant A is giving products and if initial concentration is A naught, then this is A naught minus X, which is giving maybe X amount here, isn't it? So now if at all I differentiate AT, which is equal to A naught minus X, that by dt minus of that will be equal to dx by dt, isn't it? Hmm? So this is what you will get, because from here I can write AT as A naught minus X, which is equal to A naught e raised to power of minus KT. Now if I write this X, X will be equal to A naught into 1 minus e raised to power of minus KT. Correct? And this is the value X versus T. Now it is exponentially decreasing over time, but 1 minus this value, which is smaller, should increase. Correct? So the increasing value would usually go this way. Understood? Right. Sometimes the question would be given based on the decomposition of peroxide using KMnO4. For instance, if you have H2O2, it is giving H2O plus half O2. Let's say initial concentration is A naught, and now it has become A naught minus X. So this will be X by 2, correct? So you could always relate A naught with respect to, how much oxygen that has been released. That can be related with respect to how much amount of A naught that has been consumed, correct? Now, A naught consumed can always be related with how much we are using KMnO4, and every time we titrate that H2O2 at different times and see how much it is being used. Clear?
Yes.
Right. So, in that case, what we can say, see, this will be for A naught number of moles, N into V naught is the number of equivalents used. Correct? Now, can I say that for 80, this many equivalents will be used because the volume used is different. We are not changing the
Yes.
concentration. So, which means the ratio of H2O2's concentration A naught by 80, correct? So, that will be same as V naught by VT. So, this can be replaced because it's a ratio. We don't have to worry about molarity. We just have to check out their volumes. Understood?
Yes.
Now, notice A giving 2B plus C if all of them are gaseous reactions. Okay. If all these being gaseous
Yes.
reactions, then K of the reaction in terms of T, P naught, and PT, if this is what we need to represent. Got it? So then what we can do?
Yes.
So initially it is P naught, nothing is there in B and C. P naught minus X, 2X, and X. So now the total amount of pressure will be P naught plus 2X. X can be written as PT minus P naught by 2. Okay, beta?
Yes.
And when it comes to K of the reaction, if you, since you're writing in terms of pressures, I can write initial pressure by pressure at time T. That can be written in terms of the kinetics.
Yes.
Okay. And now instead of X, if you substitute this value, this is the equation you will get.
Yes.
Clear?
Yes.
Right. Check out case 2 also. K of the reaction in terms of Pt and P infinity. P naught, then P naught minus X, 2X and X. Pt is given this much, X is given this much. P infinity is equal to 3 times of P naught. P naught, time infinity means what, beta? That is when the entire, after the entire amount of time, when the entire A is completed. Correct. So then that is the time taken. So this will be 2 P naught and P naught will be the pressure present. So P infinity will be equal to 3 P naught in that case. Okay. So P naught can be written in terms of P infinity by 3. So imagine if at all I have only PT and P infinity. So I can use those terms here and get this type of equation. Clear? These two are very, very commonly asked areas how to represent in terms of total pressure and P infinity or total pressure and P naught. Next one is about hydrolysis of sugar. Suppose if you have a sugar cane added to water, it will become glucose and fructose. The most interesting part here is initially if you have a naught amount, now after some time some X amount is lost, then the glucose and fructose will always be in the same molar ratio. So they will be X and X only. Okay.
Yes.
So suppose if pure form of sucrose is going to give you a dextro rotation of certain angle theta, and glucose is giving a dextro rotation of some angle theta, and fructose is giving an muta rotation of sorry, optical rotation of levorotatory L. Rate can be written in terms of K into concentration of sucrose into water, correct? And since water is being normally taken in sufficient quantity, and even if there is a small quantity of water, the concentration is very high. So hardly concentration of water changes. So these two can be multiplied together to show as a new constant. So it is only sucrose raised to power of 1 is the rate. So it is called as pseudo first order kinetics. Such kind is called pseudo first order kinetics. So K of the reaction is equal to 1 by T ln A naught by A naught minus X. Clear?
Yes.
So you can see if at all we have only sucrose, A naught will be directly proportional to R naught. Okay. So A naught minus X is proportional to A naught minus x by A naught into R naught. Okay. Why I'm saying so? See, for example, when only sucrose is present, these are not present. So rotation is only because of this A naught. Correct? So that R naught rotation is directly proportional to A naught. But now when you have A naught minus X, the rotation is coming because of sucrose also, fructose also, and glucose also. So that's why we write that part as for A naught, if R naught is the value, for A naught minus X, how much should be the value actually? It should be A naught minus X by A naught into R naught. That should be the value. So if it is for 2 A naught, how much should be the value? If we are writing only for glucose and fructose, and there is no sucrose in that case, so let's say that is proportional to R infinity. So if 2 A naught is giving R infinity, for one glucose and fructose molecule forming, how much will be the optical rotation? R infinity by 2 A naught.
Yes.
So if for 1 mole it is this much, for 2x how much it will be? R infinity by 2A into 2x. So now we can get what is the total rotation after time t. So A naught minus x by A naught into R naught. Clear? Next, plus R infinity into x by A naught, that is equal to R infinity. Correct? So this is the total rotation after time t. So if I add all of that, you will get A naught by A naught minus x is this formula. Honestly, you don't have to worry about how we got this. Also, you need to remember directly what is the formula. Okay. R naught is the rotation of only sucrose. R infinity is the rotation of only glucose and fructose after infinite time. RT
Yes.
is for all of them. Okay. Now, next thing you need to learn is about hydrolysis of ester. When it comes to ester, ester is also pseudo first order reaction. Okay. But it requires a catalyst for making the reaction more in the forward direction. So suppose I have A molar HCl or A molar H2SO4, you know what happens to T50. Got it? So usually what you will notice here is as the concentration of H plus increases, okay, you know, as the concentration of H plus increases here, the rate constant will start increasing. Got it? So one thing which will get influenced with respect to change in one thing that will get influenced with respect to the change in concentration is the rate constant itself. Okay. So higher the concentration, more will be the rate constant. So that's why K of H2SO4 is greater than K of HCl.
Yes.
Which means what happens to the T half beta? So T half of HCl should be greater than T half of H2SO4. Clear on that?
Yes.
Right. Okay. Next, for first order, there are two important things we need to learn. What is parallel reaction? The other one is series reactions. Parallel as in same reactant, only one reactant is giving two different products at two different rates. Got it?
Yes.
In that case, how do we define rate law? What is the concentration B by C value? What are the individual concentrations? And more importantly, what is the fraction of A with respect to you know uh, B? What is the fraction of B with respect to overall B and C? And what is the fraction of C and vice versa? Clear? Now, how do we get all these values? See, you know that minus dA by dt, correct? Minus dA by dt will be equal to, because the rate is because of these two reactions, I can write it as how much is the rate that is been gaining by B and how much is the rate that is gaining by C. Sum of those two should be the loss of A. Can I write that?
Yes.
So rate of B will be equal to K1 into A, because that is the only way B is gaining, and
Yes.
rate of C gain will be K2 into A. That is the way it is gaining. Correct? So we can write it as K1 plus K2 into A. Okay. K1 but K2 we can write it as K overall. So K overall into A. Okay. We can write this as K overall into A. Clear? So now, if at all I take A onto the left hand side, so I can write it as A naught to AT minus dA by dt, that is equal to K overall into A. So K overall is equal to 1 by T into ln A naught by AT. Clear?
Yes.
And now, this is the rate constant overall. Yeah. Have you noticed something? When I write rate of B by rate of C, rate of B is K1 into A and rate of C is K2 into A. So AA will get cancelled. So can I say that rate of B by rate of C, which is equal to dB by dt by dC by dt, that is equal to K1 by K2,
Yes.
right? And you know that for a small amount of change, this dt can be cancelled off. So what is left now? dB by dC is what is left, correct? So we'll have dB
Yes.
by dC. So dB by dC is equal to K1 by K2. Okay.
Sir, in the first step, why did we take it as first order?
Where? Here.
Yes.
Suppose if there is a loss of A, okay, let's say 2 moles, total it is losing 5 moles. He is losing 5 moles. Out of which 2 moles it is lost to B, 3 moles it is lost to C. Correct? So how do we write the rate of change of A beta? We'll write it as 5 moles changing with respect to time. Correct?
Yes.
Can I not write this as rate of gain of 2 moles with respect to time for B and rate of uh, sorry, I mean rate of this is A and B, C by T, because here this is losing total 5 moles, which is coming from 3 plus 2. Yes or no? So whatever the rate that has been gained by B, correct, and whatever the rate that has been gained by C, that is because of the loss of A only. Hmm? Clear, beta? Now I can write dB, you know, the equation for dB by dC is equal to K1 by K2. This is the equation we have. Okay. So from here, if at all I integrate that, so I can get this as B by C is equal to K1 by K2. So at any point of time, right, at any point of time, we will see the concentration of B and C ratio will always be equal to K1 by K2. Agreed?
Yes.
And AT is equal to A naught e raised to power of minus K overall into T. Hmm? Okay. And imagine initially, let's say I have 10 moles of A. Now I have left with 5 moles and B has become 2 moles and C has become 3 moles. So can I write this or
Yes.
no? So the initial concentration
Yes.
of A can be written in terms of concentration of A, B, C after time T. Correct?
Yes.
So now A naught is this much and BT plus instead of C, I can write it as B into K2 by K1.
Yes.
So writing that back here, you will get everything in terms of B now. Okay. So once you get everything in terms of B, you can calculate what is the value for B, and this is what you will get. Again,
Yes.
once you get B, substitute back it for C, and you'll get this value. I want you to mainly focus on the coefficients. What do we have when you have it in B and C? Clear, beta?
Yes. Sir.
And once you get B and C here, now notice what is the fractional yield of C. See, fractional yield is how much amount of C that has been formed with respect to B plus C. This is fractional amount of yield. Now this factor is common in B and C, so that can, because it is a
Yes.
ratio, you can delete that. Hmm?
Yes.
So the only factor that is left is K1 here and K2 here. So therefore K2 by K1 plus K2 and percentage yield is K2 by K1 plus K2 into 100. For B it will be K1 by K1 plus K2. Done?
Yes.
Right. And you know that K overall is equal to K1 plus K2 and K1 and K2, if these are two, if I write that same K1 and K2 in terms of Arrhenius equation, you know what is Arrhenius equation, right? So A1 being the pre-exponential form, A2 is being the pre-exponential form. Both of them are at two different rate constant at different paths. Different paths will have different uh, activation energies. Clear?
Yes.
Putting all of that into perspective here, so you can say K overall is equal to K1 plus K2, so addition of these two. Hmm? So K1, K overall can be written as A overall into e raised to power of minus E overall by RT. And if at all I had differentiate this ET, I will get this as E overall by RT. And you notice that A1, if at all I differentiate this one, K1, I will get it as this value, right? So if you differentiate this, what do I get? I'll get the same value, right? So all I'm doing is this one. I'm differentiating d of k overall by dt is equal to d of k1 by dt plus d of k2 by dt, correct? Okay. So if at all I differentiate that part here, so I will get this equation, and this equation.
Yes.
A lot of things are constant, so you will see overall everything will get removed out, and you will have E overall, activation energy overall is equal to K1 EA1 plus K2 EA2 by K1 plus K2. This is what you will get.
Yes.
Finished? Likewise, you'll also get as E overall square is equal to K1 EA1 square, K2 EA2 square by K1 plus K2. Any doubt? Notice, if this is how it is been given, A is giving 2B and C. And you know that concentration of B by C should be equal to 2K1A by K2 into A, correct?
Yes.
Why 2? Because you're getting 2 times of B here, isn't it? So this will be the ratio now. So the percentage yield of B will be 2K1 by 2K1 plus K2. Okay. Let us understand what is sequential reaction, where A is giving B, B is giving C, and so on. Minus dA by dt can be written as K1 into A. Okay. A in
Yes.
terms of Arrhenius equation can be written as A naught e raised to power of minus K1 into T. Okay. So if this is A naught and then we have AT, so AT would give us BT and CT here after some time. Yeah.
Yes.
Now notice when it comes to B, the rate of change of B is gaining in forward direction and losing in the sorry, gaining from first reaction and losing to the second reaction. Correct?
Yes.
So gain can be written as K1 into A, loss can be written as K2 into B. Okay. So now if I bring this to the left hand side, I will get dB by dt plus K2 into B is equal to K1 into A.
Yes.
On solving this equation, you will get Bt is equal to K1 into A naught by K2 minus K1 is equal to e raised to power of minus K1 into T minus e raised to power of minus K2 into T. Okay.
Yes.
And A naught is equal to AT plus BT plus CT. This is what we learned earlier already. Okay. Now notice this carefully. So if at all I need to find out how much time does it take to reach the maximum value of B. That means where the concentration of B is the highest. Hmm?
Yes.
Right. So which means Bt is equal to K1 into A naught by K2 minus K1. Hmm? that into this value, you know. So now dB by dt is equal to 0 implies ln k2 by k1 is equal to k2 minus k1 into T max. Because if you differentiate this, this is what you will get. So from here, T max can be written as 1 by k1 minus k2 into ln k1 by k2.
Yes.
Done? Hmm.
Yes.
Now notice if this is T max, which is equal to 1 by k1 minus k2 into ln k2 by k1, how is the A changing with respect to time? B changing, C changing. See, in case of B, it will reach to a maximum value because that's what we try to find out. And this is that T max, and after that it decreases. For C, it is nothing like that. Overall the time it will keep increasing only. So the graphs could be all three if at all we club together the concentration versus the time graph, right? So concentration versus the time graph here. So you will notice either this type of graph or this type of graph. Now here it shows that the concentration of B is reaching to a higher concentration, and then it is becoming almost close to zero. While A, it is, you know, decreasing overall, but C overall the overall the concentration is always increasing. Hmm.
Yes.
So this graph is more applicable when the K2 value is far more than that of K1 value. Okay. While this graph is applicable when the K1 value is far more greater than that of K2. Clear?
Yes.
Right. Next one is about kinetics of bacteria. How do we check out bacteria? See, bacteria usually over the time increases. Bacteria or virus. So initially, if you have n naught number of particles, after some time it will become nt number of particles. Then again,
Yes.
right, dn by dt is equal to k into nt. Ntn or nt means these are number of particles at time t. Okay. So if I integrate this value here, I can get kt is equal to ln nt by n naught. So nt is greater than that of n naught value.
Yes.
Okay. So just like t half, now we call it as t double. T double is t2. So t2 will be written as ln 2 by k.
Yes.
This t max is not usually asked, but suppose if there is an equilibrium question asked, that is a is giving b is giving a at the same time, kf is the rate constant in forward direction, kb is the rate constant in backward direction. Directly remember like a formula, do not try to derive it. Formula is kf plus kb into t. Just like how we write kt, this is exactly right how you write, you know, a rate constant for rate law for first law expression. So ln into a naught by at. This is what we write. Same thing we are doing it here also. K is kf plus kb into t is equal to ln x equilibrium by x equilibrium minus x. Alright. So please remember this formula directly.
Yes.
See the second order kinetics. A is giving products minus dA by dt is equal to k into a square. Okay. Now, if at all I take
Yes.
a square to the left hand side and try to, you know, integrate this, so I will get this as 1 by at minus 1 by a naught is equal to kt.
Yes.
At is equal to a naught by 2, so t50 is equal to 1 by k into a naught.
Yes.
Finished? Hmm. And check out second half. I mean half life. Half life will only decrease here because you can see it is directly inversely proportional to initial concentration. Okay. Hmm. Just a second, beta.
Yes.
Right, beta. See the dependency of rate constant with respect to temperature. It is given first by Arrhenius, which is purely empirical form, given as rate constant is equal to A raised to power of minus EA by RT. If I take ln on both sides, I'll get an equation of a straight line where we can plot between ln k and 1 by t. If at all I differentiate this equation with respect to temperature, I will get this as EA by RT square and rest will be K only. Now you know that K is a positive value. E naught by RT square is also a positive value, which makes this constant as, I mean this first differential as positive value. Okay.
Yes.
If at all I differentiate it one more time, correct? So I'm getting it as K EA by RT cubed, and this is coming out to be minus 2 plus EA by RT. Okay.
Yes.
Now here is interesting part, that is this might be positive or this might be negative. That depends upon EA by 2R versus T. Correct?
Yes.
So that means if temperature is less than EA by 2R, it is positive. Temperature is greater than this one, it is negative. Correct?
Yes.
Can I say that the value of K will keep going like this and suddenly change its concavity at one point, which is that point? It is a temperature at which it is becoming EA by 2R. Correct?
Yes.
Now I can write ln K2, ln K1, these two in terms of two different temperatures, and if I subtract them, then I will get this as 1 by T1 minus 1 by T2.
Yes.
K value depends on these two parameters EA and T. If the activation energy increases, then also K value increases. Okay.
Yes.
If the temperature value increases, then also K value increases. Okay.
Yes.
Now if you notice, I have A to B and C to B. Okay, C to D. Let's say C to D. Two equations. Two of them have two different activation energies. Both of them are going from temperature 300 to 310. Okay.
Yes.
So ln K2 by K1 can be written as EA into 10 by R into this value. Same is the case here also. Okay. Now there are two cases here. If EA1 is greater than EA2, then this log of K first equation, that is A to B, will be greater than C to D. Correct. This is
Yes.
when EA is greater than EA1 is greater than EA2. Okay.
Yes.
Therefore, if at all I plot ln K versus 1 by T, okay, and if the graph is given EA1 is greater than EA2, then obviously EA1 will go like this, EA2 will go like this. Okay. You can notice based on the negative slope, higher the value, that means it will have more negative slope. Okay. This will have less negative slope. Clear?
Yes.
Next point is temperature coefficient. See, if you are finding the rate constant after every 10 units of increase in temperature, then that rate constant with respect to the original rate constant at temperature T, that is defined as temperature quotient. And usually, as the temperature increases, the temperature quotient will decrease. That means if you keep on identifying for every 10 degrees, but at two different temperatures, correct? So if you are going from 10 to 20 and 20 to 30, then 10 to 20 will have a larger value compared to that of 20 to 30 in terms of temperature quotient. Clear?
Yes.
Temperature quotient itself, value, the value of temperature quotient itself is usually found between 2 to 3. Minimum is 2, maximum is 3. Okay. So which
Yes.
means if at all we take this one for every 10 degrees of raise here. So in this case, I can say the maximum amount of mu that is changed will be 2 to 3 units. The raise of K2 can be written in terms of K1 into mu. Okay. But it depends upon what is the temperature you are talking about. If between two temperatures, let's say I'm talking about 10 to 40. 10 to 40 is basically three intervals, right? This is 10 to 20, 20 to 30, and 30 to 40. Correct? So here you will get one mu one, which is same. Here also you will get mu. Here also you will get mu. So it should have supposed to be mu raised to power of 3. This many times of K1 is what you should have a rise in K2. Make sense?
Sir, could you?
Suppose for every 10 degrees there is a rise. Okay. Let's say I started with 10 degrees Celsius to 20 degrees Celsius to 30 degrees Celsius to 40 degrees Celsius. So from 10 to 20, at 10, the rate constant was K1, K2, K3, and K4. Let's say these are the rate constant at different temperatures. Can I say that K2 will be equal to mu times of K1? Correct?
Yes.
And K3 will be equal to mu times of K2. And K4 will be equal to mu times of K3. Considering in all these three cases, the mu change is same. Mu is constant. Okay.
Yes.
So in that case, what can I write? Can I not write K4 is equal to K1 into mu times of 3? And how did we get that 3 here? Because it is for every 10 degrees rise, correct? So which means
Yes.
temperature T4 minus temperature T1 by 10. That is how you got it as 3, correct? And that's what we have replaced for mu. Clear? That's how we got this formula. Clear, beta? Typically, if you want to check out what are the units of K, it is mole per liter raised to power of 1 minus n and time inverse. Okay?
Yes.
Clear? See, what we discussed is as per theoretical, empirical idea, which was proposed by Arrhenius theory. Now, there is one more theory which is more uh, collision based. So, you can see collision theory wise, rate of the reaction can be equal to total number of bimolecular collisions per unit time per unit volume into how much is a fraction of reacting particles. Got it? For instance, if you have Z11 is the total number of bimolecular collisions, that into e raised to power of minus Ea by RT is the fraction of particles which are crossing the energy barrier to form products. Okay. If these are the particles which are crossing the energy barriers to form the products, then Z1, which we learned in states of matter, that is how to figure out the collision frequency, that is equal to 1 by root 2 pi sigma square u average into n by v square. Okay. This capital N can also be written as number of moles into Avogadro's number, correct?
Yes.
So instead of that N, I replace that. So I will get number of moles by volume. I'll get it as concentration, correct? So that's why it is concentration square into Na.
Yes.
Okay. So now you can see rate of the reaction will be equal to how many total number of bimolecular collisions multiplied by the fraction of reacting particles. This is how we defined it. Okay. So Z11 into this factor. Clear? Okay. So Z11 is this. Rate of reaction will be this. Now, these values, Sunny, observe carefully. All these are constant values, correct? Except
Yes.
except for this c square. Remove that c square away. Then rest all of them are constant values. That entire constant together is what we call it as a rate constant. Understood now?
Yes.
So when you write the rate constant here, with respect to u average also, average speed of particles is how much? 8 RT by pi m. So we will get again one entire constant as a1, and you will also have e raised to power of minus ea by rt, that is the one, into, you can see there is root of temperature also as one particle, one parameter here, okay? So k
Yes.
of the reaction will come out to be like this. While a dash into root t together was combined together as an a part, right? As the a value in Arrhenius equation. Understood, beta? That's
Yes.
the difference between Arrhenius and collision theory. Okay. As per collision theory, temperature is a dependent factor, but as per Arrhenius theory, K is an independent of, sorry, I mean not K, A is an independent factor of temperature. Okay.
Yes.
Next. Rate of the reaction overall can be always written as Z11 into this exponential factor into a factor P. P is known as the probability factor. That is, what is the probability that these particles will convert into products. Got it? So that
Yes.
factor will be between, usually that factor will be between 0 to 1. Okay.
Yes.
But now there are two problems that you will usually face. If theoretical value is greater than the experimental value, if the rate of the reaction you found out, which is this one, okay, using this formula, you figured out that the rate constant theoretically is greater than that of experimental value. Okay.
Yes.
If theoretical value comes out to be greater than that of experimental value, okay, it must be the case when p is actually less than 1. Probability factor is actually supposed to be less than 1. Okay. If theoretical value is less than that of experimental value, then probability factor has to be greater than 1. Okay. Now these are the two straightforward statements I suggest you to remember, because this is how it has been asked directly. Okay. Well, we can discuss, in theory what all idea behind this, but we can do it based on a problem. Okay. Clear? Right. So last thing, if you notice, usually whenever we talk about activation energy part will be somewhere here after crossing just what do you say, number of particles wise. If you compare both of them, then this is what you will notice, that is number of particles dn by de by 1 by n. This is a fraction of particles which are crossing the barrier. If you need to check, these are the total number of particles with different energies. Now when particles reach to this energy, that means we say these are the particles which are responsible for forming products. And that's why you see at lower temperature you have less density, which means the particles which will cross over the barrier is less. At higher temperature more number of particles are observed. Okay, beta. Next, what are the terms you need to know from a reactant to the product's point of view? If you look at it, the overall energy right from 0 to the highest peak point, that is called as threshold energy. The first one is called threshold energy. From the reactant's energy to the high maximum height where it can reach, that is called activation energy. But this is activation in the
Yes.
forward direction. From products to this value, that means it is activation in the backward direction.
Yes.
And delta H of the reaction is nothing but this product's energy minus reactant energy. Okay. Or because it is supposed to be positive. So, or I can write it as, product EA of this one, delta H, clear? Uh, Delta H of reaction can also be written in terms of minus of, you know, minus of, because it has to be positive value. So which means it has to be minus of EA backward minus EA forward. Done,
Yes.
isn't it? So which means it is simply EA forward minus EA backward. This is how you can get it as positive value. Understood? Anything, any doubt here, beta? Right? So these are the terms you need to learn it from kinetics. Clear?
Yes.